today. I'm sorry about my blunder last week, but our talks in art is Ali has been at TTI now for in some capacity. Has been done a bunch of work at the intersection of algorithms and fairness and other social issues, and we'll be talking to us about some fairness and learning augmented algorithm design.
Thanks, Matthew. Thanks everyone for coming. I'm going to talk about algorithm design in the AI age, and it will be hopefully clear what I mean by that. Okay, so over the last decades, maybe we have seen machine learning, especially deep learning, and recently LLM has demonstrated remarkable performance in various applications and domains. And in many of these, even they are now beating the human performance. For instance, if you look at the object or speech recognition, by now, I mean, the state of the art is, in some sense, is beating the human, even the human performance. Another good example maybe is machine translation. So that, I mean, thanks to just the recent development now, somehow we can easily translate the text and just, in some sense, they are bridging this linguistic gap globally. These are very effective. And I mean, there are also more recent ones, and there are some that are capturing media attention a lot. For instance, like AlphaGo, that an AI system could just beat the world #1 Go player, and that was kind of impressive because it's. I mean, the Go is like a complex problem that people usually thought it's too hard for maybe AI to be effective. And actually, I mean, more recently, now talking about AI advancement, I mean, the ChatGPT things or DALL-E by OpenAI, I mean, are very impressive in a sense that we may expect that they change actually the future of computing and even beyond that. And I'm sure that, I mean, you'll have a lot more examples like that. Just, I mean, maybe 2 days ago there was this alpha geometry that could solve basically the geometry problems in IUI, which is considered as very challenging problems. So I mean, we all agree, I mean, they're very effective. But at the same time, there are serious concerns about the ethical aspects of this advancement. And as we have now automated AI or algorithm systems, now we should also be very careful about what it implies to the human that are interacting with it. For instance, there was some concerns about the performance of face recognition, and it was observed that there are some clear racial biases, gender biases, or age-related biases, and so on that we can think of in these automated systems. And I mean, there are many parties that are working to fix these sort of problems. And it's not only about face recognition, it's also the same for the speech recognition. For instance, the performance for state-of-the-art tend to be much better for male speakers than female speakers. So there are some clear biases here. And for the machine translation also, same thing can happen. For instance, they realize that these systems often default to gender stereotypes when they're translating a gender-neutral words from a language to another language. For instance, in Turkish or Farsi, when the pronouns are gender-neutral, I mean, once they're translated to English, I mean, they tend to follow the stereotype. For instance, for nurses, they're like they translated the feminine pronouns, but for instance, for doctor and engineers, they're usually using masculine pronouns, and that is some clear biases. And it's just not about these technical applications of AI. I mean, even in more human-centric applications that humans are more directly involved with the result that AI systems are providing, there are some clear biases. For instance, if you consider the hiring process or the hiring task, I mean, there was many news articles or many instances showing that the AI systems in practice are making some discriminatory behavior towards certain groups. The same thing for loan approval. Seems to be some of these algorithms seems to be racist or so on. And the same about the college admission, about the criminal justice, and so on. So there are lots of examples. So the message is that, AI and algorithms, machine learning, they are very effective. They can do very well in terms of accuracy and all these things, but they can as well exhibit some discriminatory behavior. So, and the concern becomes more crucial when we are looking at the high-stake decisions, like for instance the hiring or so on. Okay, and this was actually so crucial that the algorithmic fairness was one of the 5 principles in this recent AI Bill of Rights released by the White House recently. So there's some basically growing awareness, and people find it very important to be careful about this all implication that AI may have, in particular in terms of the fairness and discrimination that it may impose to the human. So basically, the first sentence is you shouldn't face discrimination by algorithms, and systems should be used and designed in an equitable way. So this is basically the things that we would like to have when we are designing algorithms. Okay, and that actually has motivated my talk for today. So inspired by the success stories that I mentioned in the beginning, as an algorithm designer, I'm trying to see how we can utilize ML in design for better algorithms, to have better performance once there's some nice structure, for instance, in the input. And by just to address the societal concern and ethical issues that can raised by this AI application, I've also studied algorithmic fairness, and in particular trying to design algorithms that have equitable representation, access, and opportunity. So some sort of fairness that all this is in more detail. Okay, so the first part would be about the machine learning for algorithms, and basically how we can basically use this ML oracle in our algorithm to get better performance. So the line of research that has been introduced here was Learning-Augmented algorithm, or algorithms with predictions. So and the idea here was that we would like to use some sort of machine learning components, or you can think of some black box prediction basically, and to use it in a way that we can improve the performance of algorithms when these oracles are basically useful and informative. Okay, and it's actually, if you're familiar with this beyond the worst case analysis, it can be thought of as a direction in this line of research. So it's like one way of going beyond the worst case analysis. And it has been a very active area recently. For instance, in the past 4 or 5 years, this is a nice repository that is capturing the list of papers and this topic of a very active area in the TCS community. And the high-level idea is the following. So basically, we assume that we have some machine learned oracle that we train using the past data, let's say, and then we would like to use this oracle in a way that if that oracle gives some informative prediction about the input, then we can exploit that and get a better performance than the existing worst case guarantees that we could have without these ML predictions. But at the same time, we don't want to sacrifice the worst case guarantees that we have via classical algorithm. So even if this oracle is somehow adversarially predict the future, we would like to be able to some sort of guarantee the same worst case bound that we would have without using this oracle. Okay? So basically, better performance when there's some informative prediction or useful prediction, but even if it's not the case, we don't want it to be much worse than not using it at all. And my work in this domain was mostly on the streaming algorithm. And actually, we had the first Learning-Augmented algorithm in the streaming, and I have continued to work on this topic, and also recently on combinatorial optimization problem. Okay, so I may go back to, I'm trying to go back to this in more detail toward the end of my talk, but now let's move to the second part, is the addressing the societal concern and the algorithmic fairness. So basically, I mean, as I provided evidence, we have many evidences that algorithms may discriminate different groups based on race, gender, and so on. So, and the message is that we should be careful. We should take care of the fairness and notion of it when we are designing algorithms explicitly. Okay. So, what it means for me as an algorithm designer. So, in classical algorithm design paradigm, we usually care about some metric like accuracy, runtime, space complexity, and so on. But as I mentioned, algorithms have different implications on users. So we may also want to model those in mathematical terms and also try to capture the fairness or the effect that they have on people. And for that, I mean, people have to look at the different notions of fairness, like statistical parity, equal opportunity, and so on. I mean, one question that I will just mention here is that how is fairness defined? So, I mean, it's quite complicated question, and there's many different, and actually there are many different notions of it already in computer science. Some people have different opinion about it. And actually, this is part of the research in this area, because, I mean, there are diverse contexts and requirements. So, for instance, in some application, one way of defining fairness makes more sense, and in a different application, you may want a different type of guarantee. For instance, in lending practices, it's more important to be not discriminatory towards some race or gender. But for instance, in application in healthcare, it's more important to provide some sort of equitable access to the facilities or services that state or government wants to provide. And also some complexity of human society. That is the part of the reason we have various different notions of fairness. I mean, for instance, there are some existing historical inequities and cultural differences and economic disparities. And it's not easy to see how we should actually define the fairness to capture all these background issues. And there are much more than that. I mean, for instance, there are some technological challenges. At the end of the day, we would like to define some mathematical models. So, I mean, we have to settle on some definition. And I mean, usually, I mean, this problem, there are different stakeholders with different goals and values. So it's not clear what we want for each application. It could be different from another application. And also, I mean, the fairness by nature itself is an interdisciplinary impact. I mean, there are many different disciplines that have some say on this fairness, like computer science, law, philosophy, and many others. So, I mean, these are some reasons that we have different notions of fairness, and you will also see it in my talk. Okay, but I mean, recently, I mean, the good thing is that people are more aware about fairness, and there are lots of activities on this topic. There are by now, I mean, dedicated conferences on algorithmic fairness only, not fairness. Many interesting books, and maybe more importantly, also this AI Bill of Rights or European Union regulation on fairness. So, I mean, this is a really important thing. So, even if it is the algorithmic side of the fairness. Okay. Now, I mean, I just provided some overview of what I'm going to talk about, and now let's see it more. So, I'm going to first talk about the algorithmic fairness and the type of research that I've done in this area. So, the result that I'm going to mention here are mostly focused on clustering. And clustering is a good example to show how fairness could be different from application to another application. And it's also a very fundamental computational task and has application in TCS, ML, and many other areas. And at high level in clustering, we are given a set of objects, and the goal is to group them in a way so that the objects in the same group are more similar to each other than to those in other groups. And this similarity is usually measured in terms of some distance function. Okay. And actually, the type of clustering that I'm considering here, and it's a popular one also, is a centroid-based clustering. So here the idea is that we would like to choose a set of centers and then assign point to the closest center so that some given cost function is minimized. And just to name a few of them, few clustering of this type are the k-centers, k-median, and k-means, and they're very popular in practice. Okay, let's see what are some applications of clustering and how they translate into fairness. So clustering can be used for task of partitioning. So we would like, for instance, to partition the object or the input and then assign different benefits to the object in each of these clusters. For instance, this could be in the banking example that you would like to assign, for instance, to approve or disapprove loan applications or to assign different levels of loans to different groups. For instance, here this could be a cluster and we just approve loans for this set of people. So here, the partition itself is important. But there are some other applications of clustering that can be used for data summarization. So here we have a huge data set, and then we would like to pick and the centers in the cluster, in the centroid-based clustering, can be used as a means of basically summarizing the whole data set. Right? And for instance, you can think of text summarization or a search result. So basically, when you're searching for something, you only look at the first few results, and this can be treated as a center, for instance, for all relevant documents. For instance, here, if you search for CEO in the United States, this is the result that you get. And another important application is the facility location. It's also very important in operational research, healthcare, computational geometry, and so on. So here you have some budget to open a fixed number of facilities to serve, for instance, a community or city or so on. And you would like basically to minimize some cost across these groups or in total. Okay, so here, and each of them will lead to a different notion of fairness. For instance, in partitioning, since we are mostly care about how each partition looks like, we would like to have, if we care about the fairness, we would like to have some equitable representation within each cluster. For instance, if we want to assign the loans, maybe it's more favorable, it's more suitable for us to approve, to make sure that in the approved loan application, we have a good balance between female and male. And it's okay if we lose a little bit on the quality of the result, but satisfied with this guarantee. Or, for instance, in the data summarization, then it's become more important to be equitable with respect, to have equitable representation within centers, because at the end of the day, we are now returning centers as the summary of the data. For instance, here, we are looking, we are searching for CEO of the United States. Everyone here is male, and maybe it's a more balanced result or more fair result to add some female CEO as well. And for the other application, the facility location, as here, basically the access to the facilities are the measure of importance for people or objects. Now, maybe we would like to make sure that we have equitable access across different groups. And this has led to the min-max clustering that I will talk more about. As I mentioned, these are just three ways of defining fairness for clustering, and I have worked on all of them. And today I'm going to talk about the clustering with min-max objective, or equitable access. Okay. So why we care about this? So for clustering in general, we have many good algorithms that work very well in practice. For instance, k-means plus, doing a very good job in most applications. But there is an issue that while they have very good overall performance, they could be relatively bad for a certain group or some minority group if we don't care about for instance, demographic composition or so on. Right? So for instance, here, if you look at these square groups, on average, their distance to the closest center is much larger than the average distance of the rest of the points, or some majority group. Okay. And I mean, if we care about basically some egalitarian type of utility, then it's important for us to make sure that the inequality across different groups is minimal or is as low as possible. And this has motivated the min-max type of objective for classification. Let's see it in an example and see what you can say. So let's consider the case of voting and how to select the voting locations. So this is Chicago, and I'm going to focus on this part, and you'll see why. And these are basically the voting location from 2020. And if you look at the demographic composition in this part, I mean, this is a part that contains three demographic. There's white, black, Hispanic, and these are the locations. So if we just look, I mean, by just checking it in hand babies, there is some sort of disparity. It seems, I mean, first of all, I mean, the density is almost similar in this area. I mean, them to be quite similar. And there is some slight disparity, as I mean, it seems that there are more facilities for the white communities compared, for instance, to the Hispanic one. And actually, it was observed to be the case. So there was some studies that showing that in 2020, the minority groups had to travel further to polls compared to the white voters. Okay, and why it's important? Because they show that actually, I mean, this distance notion that they call some normalized distance is actually affecting the voting turnout. So basically, it was shown as this normalized distance increases, the voting rate will also decrease. So basically, it shows that the distance here, distance to the voting location, is a good proxy for access. So basically, to make sure that different communities have reasonable access to the voting location, we would like to basically consider this type of min-max objective to capture the access of different groups. Okay, and yeah, it's actually why we are looking at min-max. And actually, I mean, it's usually the case in the system like the voting, for instance. This is from the report and recommendation from the Presidential Commission from 2014 that they suggest that no voter should have to wait more than half an hour. So I mean, it's not exactly saying that the distance should be equal, but there are we can see this type of philosophy that we would like to provide equitable access for different communities or different people. And as Nadi mentioned healthcare last week, so I felt obliged to say something about it. So I mean, another application is like choosing, for instance, vaccination sites, right? And it was actually a big deal, I mean, maybe back 2 years ago. So, and there was also some studies showing that there is some disparity in access to these vaccination sites between different groups. And that was actually something meaningful because this basically leads to disparities in vaccination rate between different communities or demographics. And was showing that as we increase the distances, the vaccinating rate also decreases. So again, another application, min-max for cluster. Okay, now let's see actually the problem formally, now that I have motivated now. So we are looking at the centroid-based clustering, so as I mentioned, so we are picking centers. Or more formally, we are given a set of point P and parameter K, and we would like to partition the points P into K cluster. And to do that, we pick basically K centers and an assignment function from points to these centers, which is usually the closest center. And then the goal is to minimize some given cost function. And the popular ones are K center, where we would like to minimize the maximum distance of any point to centers. Or it can be K median, when we want to minimize the sum of distances of points to centers. Or K means when we would like to minimize the sum of squared distances of point centers. And I mean, if you look at this notion, you can also think of it as K-centers, like minimizing the L infinity objective, looking at the distance vector. K-median, like minimizing L1 objective, and K-mean is like L2 objective, minimizing L2 objective. And in more general, we can think of any LP objective or PV, let's say 1 to infinity. So we can just solve the problem with this more general. So, I mean, this problem is NP hard, and there are some constant factor approximation for this problem. And this is the best, I mean, up to the constant, I mean, this is the best. Okay, and I mentioned I'm going to talk about the clustering with min-max objective, and let's see what it means. And it's also defined as socially fair clustering. But it was this way to independent work by Gadiri, Samedi, and Paula, and Abbasi-Vaskar and Kata Superman. So again, we have a metric space, a target number of clusters, K. But now the points are partitioned into L group, P1 to PL. And the goal here, instead of minimizing the total cost, is to minimize the maximum normalized cost across all groups. So what it means that I want to pick K-centers, and then, for instance, let's say I pick these 3 centers, and then I compute the K-median cost for each group separately. So these are the distances that attribute to the cost for this triangle group, these are for the square group, and these are for this circle group. So I compute all of them, and my goal is just to find a center so that the maximum of these 3 costs is minimized. So it's min-max. And this will work basically looking at minimizing the maximum average K-median or K-distance across all. So just one small thing is that, I mean, this normalized cost seems to be restricted. Why normalized?
Sorry, what's the average K-median cost?
Yeah.
What is average K-median?
Actually, I meant normalized, so it's not. So basically, compute the K-median cost for the group divided by their size. So this is what they're doing. Yeah, it's a typo.
So how does it make? But the K-median is already a max, right? So why do we do? Why the K-median cost?
K-median cost is just sum of the distances, right?
Oh, sum, not
yeah.
Okay.
Oh no, it's not.
Okay, sorry. Oh, just L1 or something. Okay, sure.
Yeah. Okay, but so, I mean, normalized cost is just one way of looking at. I mean, and actually in our work with Yuri, we look at a more general way of defining it. We consider the weighted case. So instead of just assuming that the points are partitioned into L, we assume that we have L different weight function that basically showing the number of points from group I at each location. Okay. And then we try to solve the same problem. So we want to, for instance, to minimize the maximum weighted clustering cost. Right? So we compute the weighted clustering for each group separately and then minimize the maximum. So, I mean, it's just not a simple extension. I mean, it's actually meaningful and capture a richer class of problems. So, for instance, it now allows for overlapping groups. And you can also, for instance, look at a different objective. I'm not going to talk about it, but you can capture regret minimization. As if how each group is suffering compared to its optimal K clustering cost if you only want to cluster that group separately. Okay, but this is, I mean, much richer. So what we know about this problem? So the prior work showed that there exists an order L approximation for fair K-means and fair K-median, where L is the number of groups. And they also show that there is some by criteria approximation, basically if you violate the number of centers by constant, you can achieve a constant. And interestingly, I mean, this problem, I can say, I mean, it's in the natural definitions so that it has some other application. And it was being studied in terms of the robustness for clustering. So in this work by Antoni Goel, Gupta, and Nagarajan, they say that assume that you have L set of possible scenarios for your input, but you are not sure which one is going to be the input that you need to deal with. And they wanted to just compute a single clustering such that it's simultaneously working good for all of them in the worst case. It's also, again, min-max clustering. And in this work, they show that there is an order log L plus log N approximation for robust K-media. And there was also some hardness result that imply that you cannot do better than log L over log L approximation. Okay, so here, we have order L. Here we have order log L plus log N. They're not comparable. Okay, if N is small, then it's better. Well, if N is large, maybe that order is much better. And here I'm going to talk about basically our tight bounds for this problem. And this is by doing work with Yuri and Eden into separate. So first we show that there exists an order log L over log L to the power of 1 over P approximation for weighted LP socially fair clustering. So basically for the most general setting of the problem, we provide a tight approximation. So in particular, it's exponentially improved the order L approximation of the prior work on socially fair clustering. Like the work on the robust, unlike the work on robust clustering, we don't have any dependence on N. So basically our dependence is high. And it's not only working for K-median or K-means, it works for any LP objective. And it's handled the weighted case that I mentioned. It has capturing much richer class of functions. And it's tight. By the hardness result, actually, we can show that it's tight for every norm. So it's not only for K-median or K-means, but for all norms, this ratio is tight. Okay, and even in a subsequent work, we look at a more general objective function. So if you look at the socially fair clustering problem, so what we are doing, we are minimizing the maximum cost across different groups, right? And where the cost is like some LP cost, LP clustering cost for the group. And then what we are doing, we are minimizing the L infinity norm of this vector. Okay, but why L infinity? Why not some other a different norm? And actually, this has motivated the notion of PQ clustering, or what we call also cascaded clustering. So now instead of minimizing the L infinity norm, we would like to minimize some Q norm that could be different from the P norms in the inner cost function. And this is interesting because in some sense it's relaxing the fairness requirement, and you can now decide basically the trade-off between the fairness and the quality of the solution. So in more precisely, for instance, if you set Q to be equal to P, then it becomes just a standard LP cluster. So it will just forget about the min-max objective at all. And when you set it to infinity, then it's become just a socially fair clustering, or the min-max objective. So it's provide a nice trade-off between these two cases. And we call it also cascaded norm because in the inner side, we are computing the LP cost in each group, and then we compute the LQ norm for the cost vector of the groups. I'll say a few words just toward the end to talk about this notion as well. Okay, so now let's see how our algorithm for the socially fair K-median works. So again, I would like to minimize the maximum weighted K-median cost across all groups. Okay. So a natural way of thinking about designing algorithm here is to look at the LP-based approaches. So the very general recipe is as follows. So find the relaxation of the problem, find an optimal and solve the LP relaxation, find an optimal fractional one, and then try to round it. Okay. So this is not very informative. This is very general, and it's not actually a good recipe. And actually, for the case of clustering, there has been some sort of more detailed type of LP rounding approach. So they look at the fractional solution for the basic LP relaxation for this problem. And this is work by Charikar, Guhatarj, and Schmois. And then in the second step, using the fractional solution, they show that there exists a way that you can basically sparsify your instance and just only deal with the instance with, if for instance you want to do K clustering, the instance is only supported on, let's say, 2 K. So they show that there exists propose such a reduction. And beside that, they show that in the final instance, there always exists an almost integral solution. The solution that that admits a good fractional solution for which all centers are open by large values, let's say larger than half. Okay, so they have some nice structure. That's the message, basically. And then once they have it, they show that there exists a good, basically, greedy deterministic rounding for this sparse instance. Okay. But there is a catch here. I mean, once we are considering it for the min-max objective, we fail at the very first step because the basic LP relaxation for this problem has a large integrality gap. And just to emphasize that this basic LP relaxation tends to be very basically useful for other variants of clustering. I mean, it's, for most of variants that we know, I mean, this is usually work. But here, this basic LP clustering is not effective. So let's see what is this relaxation. So I have y variables for each of my my facilities or locations, indicating whether that location is a center or not. And also I have x variable saying whether a location u is assigned to a center at location v or not. So xuv is equal to 1 if u is assigned to center at v, and it's 0 otherwise. Then we can write the problem as this LP relaxation. I want to minimize this max objective that, I mean, for simplicity I write it here, but I actually should write it as a constraint to be a valid LP relaxation. And then I want the first constraint saying that each location should be assigned to a center. The second one saying that I want to open at most k centers. And the third set of constraints saying that u can be assigned to a center at location v only if the central location v is open. And then we have also negative constraint. Okay, so a useful notion here is just the fractional distance or cost for a location. So which is basically what's basically the cost of any location at any point at location u is to its closest centers with respect to this fractional solution. For instance, here, if this is u and u is assigned fractionally to these three centers, this is its fractional distance. By this value has to pay this distance, and 0.1 is paying its distance to C2 over C3. Or it might be useful actually to look at it as this assignment profile. That this is basically the fractional distance, and these are basically the support in the fractional solution, and this basically capture how u is assigned to its center in the fractional solution. So first thing that we need, I mentioned, our claim was that the integrality gap of this LP is large. And this is a simple example showing it. So here we have k plus 1 points, each with pairwise distance 1, and the number of group here is also k plus 1. I mean, this is for simplicity, and actually you can have much more points here, and you don't need actually to have n equal to, you don't need n to be equal to f, but just for simplicity, let's assume this is the case here. Okay, so we have n points, and each is just a single term. So it's easy to see that in the fractional solution, you can just open every one up to value k over k plus 1, and then each group or each point in this group is assigned to itself by this value, and just by this little value is assigned to someone at distance 1, some other centers. So the fractional distance then would be k over k plus 1 times 0, because the distance to itself is 0, and by just 1 over k plus 1, the distance would be 1, so the fractional distance is 1 over k plus 1. But it's easy to see that in any integral solution, you can only open k of this location. We can only open centers in k of this location. So there exists one location that doesn't have any centers, and that particular group has to pay exactly 1 in its clustering. So the integrality gap is basically k plus 1 or omega, and we cannot do better than that. So to see why it's the case, I mean, we can look at the assignment profile. So if it was like this, that each point was only assigned to a single center with value 1, then it was perfect. Basically, it was the integral case. It was also still fine if it was assigned to different centers, but all at almost a similar distances to the fractional distance. Then if we could just make sure that one of them would be open, then we would have a good approximation. But the bad case is really when we have a heavy tail, when with a large value is almost center itself, but there is just a tiny value that is assigned to someone pretty far from it, which was the case actually in the integral data instance. And so basically the bottom line is that if we can make sure that there is no bad profile, then randomized rounding would work almost well. And now how we can do that? So the idea is that if we can show that there exists an upper bound delta u for any location u, such that the distance of u to its center in any optimal solution cannot be larger than delta u. If we can make sure that this is the thing, then we are basically in some sense getting rid of the heavy tail. So basically this is effectively what we are getting rid of. This part of the assignment problem. And this is what we are going to do. First we guess the optimal value, and then we show that we can compute these values of these upper bounds values for any locations, and then we add them at the corresponding constraint to the LP relaxation and just solve it. Okay, so let's see maybe how we can compute these delta u values. So the high-level idea is that if for a location u, its distance to its optimal closest center is large, then if we look at the nearby points to u, for instance in this ball, then for all of these points, their distance to the closest center should also be relatively large. Okay, so if u is paying a large amount, these points also paying a large distance. And if we just now look at the cost that incurred by this point, we should make sure that these cost is not more than opt. And this is how we can get actually our bounds on the delta. Okay, so more formally, we can say that if the distance of u to cu is larger than delta u, then if I look at this ball of radius delta u over 2, for all of these points, their distance to the optimal center is at least delta u over 2. Okay, so if the contribution of just this ball is larger than the opt value that I guessed, then it means that delta u, then it means that the distance of u to its optimal center has to be less than delta u. Okay, so we can compute. I mean, I'm just mentioning it not in a very formal way, but this is basically how we are computing these values. Okay, and once we have them, we just add this constraint to our LP relaxation and get rid of this heavy tail. Okay. And now let's see how so now that we have this LP relaxation, let's see how it works in high level, the algorithm. So this is basically our main claim, that this new LP relaxation has integrality, admits a rounding that gets order of log L over log L approximation. And the way we do it, we first basically again sparsify the instance using the ideas that I mentioned earlier, and we make sure that each point is now supported by 2 centers only. And then in the second round, in the second step, we show that we can basically now randomize this fractional solution and get the approximation that I promised. Okay, and this is basically the same, basically the reduction to the sparse instance that I'm not going to talk about. I just briefly mentioned a few things about randomized rounding. So just have it in mind that if you just want to satisfy everything in expectation, that would be very easy. Just sample each location with just the fractional values that we have, and that basically does everything in expectation. So in expectation, the number of centers is at most k. The expected contribution of u to the objective is okay, is just the opt, as in the fractional solution, and everything is good. But we are not done yet, because we would like to make sure that it's hold with high probability and we get a valid solution. Let's see what are the challenges and how we can fix them. So the first thing is that we might basically sample more than k centers if we just naively sample each location proportional to its y values. But I mean, there's a fix for that. We can just undersample centers a little bit, so make sure that with high probability we are not getting more than k-centered, but still have a reasonable cost. And then, I mean, the second challenge is that we would like to make sure that after this sampling, we are going, one of these two centers are going to survive for a location view. Because otherwise the cost for this particular location would be tremendously huge. I think we have no control. And for that, we are doing some sort of dependent rounding. So basically, we show that we can increase some y variable to 1 and slightly decrease others, so that these properties hold. So at least one of them will survive for each location. And then maybe the most important thing is that we would like to make sure that the expected maximum cost across group is small. And this value could be much larger than the maximum expected cost that we can easily argue about. To handle that, I mean, what we are doing, we show that by the new constraint that we had, that we show that no point is going to be assigned to someone at pretty far distance from it. And then using some concentration bounds like Bennett's inequality and so on, we can show actually we are not going to lose more than log compared to the fractional solution. Okay, so basically this is what I wanted to mention for this problem. So we propose a new LP relaxation. We show that this, I didn't talk about this part, but this sparsification can still work. And at the end, I mean, here also we propose a randomized rounding. So unlike the previous work that usually have some deterministic greedy type rounding, we show that there is a randomized rounding, and the new LP relaxation, the new constant was crucial for this one. And then we go to this more general version, but then when we go to this PQ clustering, then we have to deal with a convex relaxation. And then actually, I mean, another challenge is that now we need to deal with exponentially many constraints. So in this min-max clustering, we only need to add one extra constraint per location, but here, I mean, it's not enough. You have to look at all subsets. So it's more complicated, and actually, I mean, we don't have a standard sort of separation oracle that we can then use the ellipsoid method to solve it. And we are actually using a rounding approach as a separation oracle for this complex relaxation. And actually, I mean, since we are now need to work with the higher norms, we also need to work with more advanced concentration bounds, like Lotto-Loss inequalities and so on. So it's more complicated, but I mean, and these are basically the two approximation regime that we can get. So it two different behaviors depending on whether Q is larger than P or smaller than P. So I'm going to skip it and I'll talk about. So the bottom line. So I talk about the fairness of algorithm machine learning, and in particular for the clustering. I mentioned that there are different notions like based on the application that you have in mind. And so this is the set of works that I have done in this area. And more recently, I'm also working on other topics like the matrix approximation, which is basically a linear algebra view of this clustering, looking at the fairness for instance, column subset selection or low-rank approximation or regression type problems. And again, I mean, depending on the application, we are looking at the different notions and so on. And another problem that I'm interested in is like the hiring problem and the fairness of it. So in particular, I'm looking at the sequential screening process and considering and studying it with respect to fairness, strategic agents, and information disparities. So I would be happy to talk about it if you're interested. So actually, I'm going to skip the Learning-Augmented as I thought I won't have enough time, but in any case, I would be happy again to talk about it. And yeah. Okay. So now let's see. I mean, I wanted to talk about the algorithmic fairness and machine learning for algorithms. And also to mention that my past research was also mostly on approximation algorithm and sublinear or massive data type analysis that actually has influenced a lot my current research. And let's see, say some last few words about the future. So I talk about the fairness, and I mean this is a very important problem, as I mentioned. One particular important application is data summarization methods. And here I would like to understand what's the complexity of for instance, the fair clustering further, and there are still some nice open question here. For instance, I mean, for the fair representation, we still don't know what's the right approximation bounds. Which in our very recent work, we show that there is a very nice connection between this fair representation clustering and well-known capacitated K median, for instance, problem. This is a problem actually known to be hard. We don't know whether that order of log K approximation, and it's interesting to see it from now, this new perspective, to see if we can have some advancement here. And there are also some nice linear algebra type problem that I'm interested to look further, and it's, for instance, in the column subset selection with a natural generalization of clustering, for instance. I'm interested to look at the different notions or different applications of fairness here. And as I mentioned, one other problem that I'm interested in is the hiring, which is more like the human-centric, direct human-centric application. And we basically, in the work with Avram and Kevin, we look at some sequential process, like the hiring when you first have some CV screening, some phone interview, pre-interview, and on-site interview, which basically you filter out candidate and each round. And basically, this is what firms over, let's say, university are usually doing. And we show that, I mean, if you want to provide some sort of equal opportunity or some sort of fairness, you can just do it by a slight modification of the existing pipelines. And there's still some more interesting questions to this topic. For instance, what happens if we consider it with the strategic agents or informations? So I will conclude my talk here, and thank you.
Quick questions? Actually, I have a few. So, what you guarantee is to give an approximation to the optimal way of doing partitioning. But if you run your algorithm, you give me a partition, some clustering, can I tell whether this is fair or not? Because it seems that the fairness here is a property of more of the algorithm than the partitioning. Is there?
So you want to have some
I mean, in what way?
Candidate or?
Well, I want to. I'm trying to see how to phrase this question. But you take all the example you said at the beginning, and you saw all kinds of partitioning where the partitioning seemed unfair. Mm-hmm. But maybe they were actually created with an algorithm that has that's trying to optimize some objective, and either that's the best you can do in that objective, or you're not even that's within a factor of whatever log n of what you can do in that best objective. I guess there are two questions here. One is, how do I tell whether that's okay in that regard? Like, I'm not the one that ran the algorithm, and the second, is this acceptable?
Yeah, I mean, I guess it depends on the application. But for instance,
so what kind of
for the voting, I mean, if we have some gap that I don't want any distance to be larger than that, I mean, you can check that.
But that doesn't ensure. It just ensures that you're within the optimal. Maybe the optimal is maybe the best they can do is a
right.
So if I have so
but it gives some evidence that this is basically the best you can do. I mean, as we are showing that this is basically.
What's the evidence? Like, if you give me a partitioning, like, how do I know that this is actually
the best? Yeah, that's a good question. I know. Can show.
Additional
last question there?
Yeah, one question. So you feel like fails clustering, so you have weights, like basically depend on the individual belongs. Considering if there are any weights, like after you create the clustering, you do a completed version, like for each cluster you have some weights depending on how how fair this cluster is or how important this cluster is.
So you mean you first run the algorithm and then?
And then when you compute the cost, there is some weight, but this weight might depend on the cluster structure.